Yeah, so this MaxQuant basic session will be about, I should go into presentation mode. Will be about, actually about the ion mobility features that were added to MaxQuant recently. So that was done because we wanted to support the new Bruker instrument, timsTOF Pro, which scans ion mobility in addition to the LC-IMS-MS that it's doing. Which essentially adds a new dimension to the data, right? So the data used to be mass, retention time, signal intensity, and now we have a fourth dimension added to this, which is ion mobility, which is like scanned on very short time scale through every cycle that you do through the mass values. So so what does that mean now? So we have instead of so instead of in conventional LC-MS, where we have the 2D input space, which is of course mass of the MS1 features in the mass spectrometer and retention time, we have in addition now as an input parameter the ion mobility index, or this can also then be translated into collision cross-section values or 1/K0. So there are many ways how you can parameterize this dimension, but essentially we can say this is like an index that is kind of indexing a new dimension that has a certain number of bin values there. So that, and this kind of index we call an ion mobility index. So we have like three independent variables now over which we record the intensity. So that makes up the four-dimensional space basically, right? So peaks and features used to be in conventional LC-MS 3D objects, so exactly these kind of hills that you've seen in 3D plots, like the intensity pattern, hill over mass retention time. And so these now become four-dimensional objects just because you added an additional dimension to your data, right? So this comes now with a couple of complications. Of course, your computational workflow has to be adapted to accommodate this new dimension, but also things like just viewing at your peaks. So that is becoming more challenging now because so we used to have these 3D objects, and these are so 3 dimensions we know as humans basically very well, right? So we can visualize things in 3 dimensions easily, or we can use heat maps to show the intensity patterns in the plane. But then, so with this added dimension, so we already are challenged as human beings basically, because so you really wanted to see a 4-dimensional object now. I don't even know how to show it with my hands. So some 4-dimensional object as a peak, which you obviously cannot do. But then you have to do things like you project, right? So for example, you could go into slices of your data. You could then look at your data at fixed ion mobility index, then you're back to a 3-dimensional feature. You could look at it as fixed mass or at fixed retention time. So you could basically slice it in any of these 3 dimensions, and then you're left with the other dimensions, right? So that's also something we can do in MaxQuant. And funny windows here that you don't see. And okay. And so that's the challenge of viewing the data. So the challenge of the analysis workflow is that, of course, now many parts of MaxQuant have to be adapted to be able to deal with this kind of data. And here you see, we saw that before. You see the main workflow steps in MaxQuant, the main computation task, in the order as they are done. And then some of them need a lot of adaptation, of course, and some of them can be just taken over as is, basically. Like, for example, feature detection will completely change now, of course, right? So one has to use new concepts to detect features. Also, the way how you prepare MS-MS spectra for the database search will also change, because now you have to project out these MS-MS spectra from higher dimensional data, right? So because we still use the Andromeda search engine on conventional spectra, and to produce them, we have to get them basically projected from the higher dimensional data, and then of course you have to know where exactly you should project and so on. So this is also will need a lot of adaptation. But then things like the search, like initial search and main search, they remain more or less the same because the spectra that the search engine will see will look exactly the same because we project them down to normal spectra. But then things like recalibration will change because we saw already that, for example, for the mass recalibration, we determine nonlinear recalibration functions of the mass that depend in a nonlinear way on the mass itself and on the retention time, right? And so now the question is, will this also depend? Will this have to depend on the ion mobility index, right? And the answer is actually yes. So we also will have to take into account an ion mobility dependent correction of the mass. And since this is TOF data, we also have to take into account an intensity dependent correction of the mass. So basically 2 more dimensions are added on which the calibration function will depend on, right? So recalibration also needs quite some adaptation. But then, for example, things like how you calculate the PSM FDR, so that again will not change, same thing. Alignments, so that might change again because it might turn out that you also need to align the ion mobility index, right? So that's an open question. Is it so stable that you never need to align it, or would that also benefit from alignment, right? So we will see about that later. Matching between runs also needs to be adapted because now we are matching these 4-dimensional objects, and we can now use actually the ion mobility coordinate to make the matching more specific, right? So because now not only the accurate mass has to match or the retention time, but now also the value of the ion mobility index has to match to have a valid matching between 2 runs, basically. But then things like protein grouping, label-free quantification, so there's not much to do. That should be transferable 1-to-1 to ion mobility data. And then, of course, since some results are now specific to ion mobility, also the writing of the result tables will have to be changed a little bit. Okay, so the first step, so let's go to the steps that we're doing. The first step that we do to analyze this data is some regridding, so that we have data points on a regular, so not necessarily with same lattice spacing everywhere, but on some kind of grid that is comparable throughout all the dimensions. So we have to, it turns out then for Bruker data, one has to regrid them in the mass direction. And so while doing this, we're also doing some smoothing in all kinds of dimensions. So we're doing some Gaussian kernel smoothing in the mass direction, and also some median summation, or median summarization into the ion mobility index direction. So that there's lots of smoothing applied before we actually analyze the 4-dimensional data. Right, so that's happening here. So how do we go on? So then what we do then is, so we just slice so we have the data cube consisting of retention time, ion mobility, mass. And so from this we take now slices. So we slice it actually in ion mobility direction. And then we analyze further these slices, which consist of the smooth data sliced. And so why do we do this? Because basically we have reduced an existing problem to an already solved problem, basically, because these slices, that's exactly what the conventional MaxQuant sees and where it does the peak detection, right? So then we do peak detection in all of these slices, and that's of course highly parallelizable. And then we get peak shapes. So that could be some part of one of these slices where you have mass, retention time, and this would be at one specific ion mobility value, basically, right? And then we do the feature detection there, and we get then like shapes that are surrounding the feature. So it's not just rectangles, but it's really nonlinear shapes that we determine there in the data. And then we have all of these shapes in all of these slices, and now we have to stitch them together, basically, in the ion mobility direction. So now these shapes, so they are then aligned in ion mobility direction. And then there's just some algorithm that looks so in the next slice is there a feature within a certain tolerance, and then these will be bundled together to these 4-dimensional peaks. So then we have the 4-dimensional peaks detected, and now can work with these. So the next thing would be to do all kinds of recalibrations in all directions of these peaks, right? So as you saw in the LC-MS, in the case of standard LC-MS data, we do the correction of systematic errors based on this first search, main search principle, so that we do a first search with Andromeda just to create these recalibration curves, right? So the results of the first search will not go into the result tables, they're just there to produce recalibration curves, and we do exactly the same thing here, right? So that's what we had before. So these delta masses that we get from the first search by just, calculating what is the difference between the measured mass that you get from this first search and the calculated theoretical mass. So this we can now do actually just in more dimensions. So in addition to the retention time and mass, we also do this now in the ion mobility and peak intensity direction, right? And then, so that's actually what the result of this, what you get out. So this is the residual error. So now you have 4 factors that the error depends on. And what you see in each of these plots is the residual error if you corrected already for 3 of the 4 mistakes, basically, right? So like, for example, this one here, let's pump this thing a bit. So where it's the error is plotted against M over Z, so that means this is the M over Z dependent error after you have corrected for the ion mobility, retention time, and intensity dependent error, right? So that's basically telling you what is actually the variance that is coming from the M over Z dependence, basically, right? And then you have all of this for all of the 4 contributions, and you see actually, so these are all plotted on the same mass error ppm scale, and then you see actually that the contribution that you get from the ion mobility dependence is actually the biggest one of the 4. So you absolutely have to make the mass correction depending on the ion mobility. If you wouldn't do that, you wouldn't get rid of systematic errors at all, basically, right? So that was crucial to do this. And also the other thing, the intensity dependence. So that's not something that we introduced because of ion mobility. This is something that we introduced because of TOF. So that's the big difference between TOF and Orbitrap. That in TOF instruments you actually have an intensity-dependent mass error, while in Orbitrap instruments, miraculously, or by design or whatever, but in Orbitraps you don't have an intensity-dependent mass error, right? So just for regular TOFs, one would have already included this contribution. A microphone for him?
So why is the mobility contributing so much to the variations? Or?
So I don't really know. I mean, we're just there to observe the data, but that's just your job when next month when you're working at Bruker, basically. Right, so data is calibrated, and so mass error is nicely shifted to be centered around 0 and much smaller than before. So next thing to do is matching between runs. So as already mentioned, the change here is that the matching between runs can now also take the collision cross-section into account. So that also has to be the same. Otherwise, you wouldn't match 2 features in 2 different runs, right? Which means matching becomes more specific, right? You have one more criterion to include or exclude the matching, basically, right? Which of course helps, right? And but for doing proper matching, you have to not. So we have corrected the masses, but so already with LC-MS you had to correct the retention times. You have to align retention times, right? And that of course we just do as before. So retention times are basically based on the time difference that you get by matching with large windows between two runs. You can then also estimate from there some kind of calibration function by following the high density region here. And then you see after we apply retention time alignment, everything is nicely centered around 0. So that nothing changed here, so that we did, before as well. But then we have now the ion mobility, and so the question is there, should we also align the ion mobility before we do the matching? And so here the answer is yes as well. So if we apply exactly same strategy that we used for retention time alignment now in the ion mobility direction, we see that in unaligned data, if we match two runs to each other with like large window, we see that the density of these match differences, so this is 1 over k0, which is just one specific way of parameterizing what we called before the ion mobility index, basically. It's a more physical way of parameterizing ion mobility dimension, basically. But then we see if we look at the differences of this 1 over, needs to batteries at some point, of this 1 over k0, if you look at the differences within these matches between the two runs, then you see that this also depends on the on the 1 over k0 or ion mobility itself. So it's off 0, so it's not it's at the 0 line, but it's also not a constant shift, but it's something you could maybe call linear in that particular example, but then you're never sure if that's going to be linear all the time. Certainly it needs some correction, and then we just apply exactly the same kind of nonlinear nonlinear function that we use for the retention time, just in case it looks worse or more nonlinear in other cases. Apply it in the same way, and then also get so on the calibrated data, then something where the error is nicely fluctuating around 0. Right? So we do. Is this a hand? No. We do recommend ion mobility alignment there. Of course, this depends on how often and when and how you calibrate your instrument, right? So this is basically freeing you from having to calibrate your instrument all the time. So essentially what we also do for the mass, because you could also say, yeah, but I could do better than what you're showing with these 10% ppm fluctuation by just calibrating my instrument every day, right? But so basically we want to provide software that frees you from all of these things that could go wrong because you forgot to calibrate something or something like this, right? So so that is just one other step basically to free you from these constraints. Right, and then, so after we do the alignment in both retention time and ion mobility direction, so that's what we get then as histograms for the differences. So this is here the retention time difference between features that belong together in two runs before and after recalibration. So you see the histogram is shrinking quite a lot. And equally so for 1 over k0, which parameterizes the ion mobility. So you actually see an even bigger effect on shrinking the histogram of the differences, right? And then allowing you to use a smaller window for the matching. Right, so now data is aligned, so we can do the matching between runs. So what does it buy us then? So here's an example of 2 hour HeLa runs, so 10 replicates. And so what you see, first of all, is that so without matching between runs, these are the blue bars, you get 5,000 something peptides, and then you see what this not peptides, this number of proteins that you can quantify in each of the samples. And then this is what you get on top then in each of the samples. And interesting is actually this plot here, which tells you how often do you see a certain protein in each. This is better. Smaller but better. Yeah. So this is telling you how often you see a certain protein in n out of the 10 replicates, right? And so there's ones with matching between runs and ones without matching between runs. So you see basically the number that of no, it's also I think. So you see that the number of proteins that you see in all 10 out of 10 samples is actually increasing by 1,000. So you get 1,000 more proteins that you see everywhere, basically. So matching is doing something good in these samples. So that's just another example where we applied matching between runs. Now it's 20-minute plasma sample runs, and it's 220 of these. And this is just, again, the increase of proteins that you can quantify in each of the samples, or it's the number ones in blue with without match between runs, and then they're actually sorted by this number. And then in orange with match between runs, and on the right you see exactly the gain that you get from match between runs, which is substantial, so reaches 130% in some of the runs, but on average is somewhere in the range of 80% or something like this. So really in these short plasma runs, really substantial gain in number of proteins that you see in each of the samples and can quantify there. Right, so then, so what we were hoping for is that the number of false positives that you get now through the matching should decrease because of the added information for each match coming from the ion mobility. And that we were trying to investigate in this plot here, where I think I need to explain a little bit what's happening here. So we match now basically without retention time constraint. And we change so on the x-axis we change the ion mobility window. So it's 0 here, so big here. So if you come from here to here, the ion mobility window is getting smaller and smaller and smaller, basically. So it should be more and more specific match, basically, right? And so on the right side, basically, you don't have any constraints. So you don't constrain on the retention time and also not on the ion mobility, right? And now, so we just to have some criterion for evaluating this, we just call. So this is not really true and false matches, but we just call something that has a close retention time difference, true match, and something that has a wide retention time difference, a false match, because if it has a wide retention time difference, it's likely to be wrong, and if it is nearby, it's likely to be correct, right? And so we actually split at 42 seconds, so everything that is below 42 seconds, we just call now a true match. So don't misunderstand this. We don't mean to say that this is a true match, so we just call it a true match, right? Because it's likely to be a true match. And the ones with larger retention time difference than 42 seconds, we call a false match. And then we just count how many these are. So we calculate the percentages. So they start high on the plateau here. And then you see that actually the false matches get reduced earlier than the true matches, basically, right? And then if we then normalize these two curves to be on top of each other at the asymptotes and divide one by the other, this is kind of a measure of the gain in quality or the gain in specificity that we get through the ion mobility window, right? And then you see with no ion mobility window or completely open, there should be no gain by definition, basically. And then if you decrease, you see there's a threefold gain in specificity that you get from applying the collision cross-section as an additional criterion for the matching. So it's doing something good, again, also not just in sensitivity, but also in specificity. Right, and then so we then applied label-free quantification. So that's so 3 species set up that you might know from other studies. So where you basically mix, you have replicates, and then each of these replicates is a mixture of 3 species, and then you have 2 replicate groups, and then you know that between these replicate groups, this species should have this and this ratio. So I think this has been done in a couple of contexts already. And then you see that, so obviously the vertical lines are the expected ratios, and you see that everything is nicely clustering around these. And so the left and right is again with and without matching between runs. So you see then, so here with match between runs, you get a lot of proteins that are low abundant that you don't see here without the match between runs switched on. So it's working again, so one can use label-free quantification for that. And that appears to be the last slide, so thank you for your attention.